In this module, we're going to quickly introduce the concept of Stokes' theorem. So let's start by tying this back to, again, our electric field journey. Remember, in the electric field, we had Gauss's law. And then from that, we tied some concepts together to introduce the divergence theorem. So as a quick review, we had Gauss's law, which said that the surface integral of d by ds is going to be equal to the charge enclosed. And we also knew that the charge enclosed could be evaluated by a volume integral of the charge density. And the charge density is also the divergence of the electric flux density. Therefore, you can rewrite the closed surface integral of d by ds as a volume integral of the divergence of that same vector field across the same volume. So here we're going to do the same thing with Ampere's circuit law to get Stokes' theorem. So this is another trick that works for all vector fields. Just remember that in Ampere's law, so now we're reviewing Ampere's circuit law, we knew that h dot dl is going to be equal, if you do a closed line integral of h, you're going to end up with the current enclosed, which is also going to be equal to, which we can also rewrite as the current density integrated over the surface, right? Now, remember that once we had Ampere's current law in integral form, we can also take it in differential form, where this closed loop integral, line integral, turns into the curl operator. So you have the curl of h, and what does the curl of h equal to? That's right, it gives you the current density. So you can just, in the manner similar to what you had, where this is charge density and you plug the divergence of d in, you can also plug the curl of h into this expression where the current density is. And then the result is Stokes' theorem. So Stokes' theorem, simply stated, is that the line integral of h dot dl is going to be equal to the surface integral of the curl of that vector field. And this is similar to the divergence theorem. This is a way to simplify the problem a little. So remember, the divergence theorem sometimes comes in handy because if you want to do the closed surface integral, sometimes that's a little harder to do, but you can take the divergence and do a volume integral, which is sometimes easier. So same thing here in the case of a line integral. Remember when we were first learning line integrals were more painful, right? The fewer the integrals, actually the harder it was. So the line integral was kind of towards the top of things that were hard, especially when the field is not conservative and you actually have to follow the path. So in this case, one nice way to do is if you can take the curl operator, then you change this line integral into a surface integral, which can sometimes be easier to do. And similar to the divergence theorem, which is over here, both of these are true for all vector fields. So these are tricks that you can potentially use in other settings, in other disciplines where you have vector fields, to impress your friends.